Hi, I'm James Mora, Senior Editor at Electronic Design. I'm here at APEC 2026 with Kannan Soundarapandian.
Yeah.
He is the VP and GM of the high voltage product line at TI, and he is working currently on the developing high voltage 400 to 800 volt power architectures for data centers. So, Kannan, I wanted to ask, how is the shift to high voltage power distribution changing the overall architecture of the rack? Like, if you open the door of one of these systems, sort of, how does it look different from what came before?
That's a great question, James. It's going to look almost completely different, I would say. So with every new generation of GPUs or LPUs or any XPU really, the power need continues to increase, and you could think of it as almost a 70-point increase generation to generation, which effectively means the problem to solve right now, which is getting that kind of power into a small few centimeter by few centimeter piece of silicon, is getting significantly harder, almost on an exponential curve, I would say. So one of the only ways to actually solve that problem is by getting higher and higher voltages closer to where that power is being consumed, simply because of I square R and certain laws of physics that you simply cannot break, right, from an efficiency standpoint. But if you think about it, that means if you get 800 volts all the way close to the backplane of a server rack, that's a very different animal from having 12 or 48 volts, which are human safe, versus 800 needs to be protected in a very different manner. So now everything better be completely uncluttered, completely deterministic, and very, very clean from the entry point of 800 volts at the backplane all the way down to the processor. And in later generations, we'll actually see that 800 volts get to within a few inches of where the processor itself lives. So these are very exciting times, and that's a completely different architecture from anything that is running in production today.
So you mentioned that in the future, the 800 volts is going to get very close to the processor. Where
Yes.
is it sort of today?
So today, if you think about it, 800 volts isn't even necessarily in the data center in that capacity right now, right? So today what you have is regular AC power coming in through the walls,
sure.
and then we basically have power supplies that go from AC DC down to say a 48 to 54 volt backplane, and that is what gets fed into the servers. 400, 800 volts, all these new line voltages that we're talking about are the beginning of a completely new era in how we design and consume power in the data center.
Okay. So to understand sort of, I guess, like I said, what you see when you open the door of one of these systems, which, like you said, aren't necessarily deployed yet, but are getting there. Can you maybe walk through some of what we see here with the sidecar and the other components, just to give people an understanding of what the actual building blocks are?
Absolutely. So if you look at it, if you imagine this is where the energy comes into the wall, right? This is three-phase AC, 480 volt RMS AC voltage, and you'll actually see that this is the power supply that we've got. It's a 30 kilowatt power converter that effectively puts 800 volts out. Now we also have an 800 volt capacitor bank, because when you have racks consuming this much power, you'd better have some sort of localized ability to store energy also. This, for example, is an 800 volt capacitor backup unit. These are the capacitors that go inside it from our partners, and that 800 volts then gets into effectively a hot swap solution. Now why this is necessary is these are dangerous voltages. When you plug a server into that backplane and take it out, it needs to be very graceful, which means it cannot cause disruption to everything else on the rack. This allows that to happen in a very graceful manner. And then you've got, say, we have one example over here. This is an 800 volt to 6 volt DC-DC power supply. It's capable of putting 20 kilowatts of power out there. You can imagine this as sitting somewhere very, very close. It'll be on top of the motherboard, but it'll be very, very close to where you have the CPUs and the GPUs itself. And that's what I meant by you're able to get 800 volts somewhere very, very close to where the GPUs itself live. Now this is not the only way to do it. There's also other voltages you can go to. And at that point, you then get into the next stage, which basically takes that, what we call an intermediate bus voltage, and delivers that as core voltage to the processor itself.
So I wanted to focus a bit on the 800 to 6 volt DC-DC power converter, since that's a sort of new innovation that anyone here will see, TI and other companies sort of working on similar, very large step-down converters. Can you maybe talk about some of the technical challenges that sort of arose with that, and maybe some of the solutions that you developed to make it work?
Yeah, so I mean, if you ask me to pick, there are so many challenges over here, right, that we needed to solve, and it's been one of the more exciting, the problems that we've had to solve in my career, at least here at TI. If you look at the form factor, And if you look at just how much power density we're packing in, that's a good 2 kilowatts per cubic inch of power delivered if you think of it that way. Which effectively means, and especially as you go to lower voltages, which is what is necessary as you deliver more and more power to the GPU, the amount of current you need to deliver for a certain power level obviously increases. So if you think about just one half of this board here, that should be able to provide 1600 amps. This is an insane number, but that is what it takes when you want to deliver the insanity of a half a megawatt to a megawatt now in next generations into a rack the size of a refrigerator, right? So the biggest problem I would actually say is getting it all, first of all, getting the power density in a long-lived manner. It has to last over lifetime. Continuous power delivery, high quality, and being able to tolerate extremely large amounts of current coming out of one module like that.
Okay. So I wanted to ask sort of a broader question. I think Nvidia is maybe the biggest company at APEC that's not actually at APEC this year. And with them being sort of the leader in the AI compute space, I'm wondering sort of how much influence you see them sort of exerting on the future of power electronics. And is that accelerating innovation in certain areas or specific types of components or specific technologies? Maybe it wouldn't be moving as fast if they hadn't sort of started paying as much attention to the power space.
It's a good question. Data centers as a whole, if you think of it, right? I mean, there are major hyperscalers that are coming online, not just coming online, they're already online, but there's massive amount of growth in this particular field. So the speed at which this is being driven is something I've not seen before, at least. I mean, we're talking about a base that used to be a little less than 125 gigawatts of total power consumption for the entire data center space, growing by 40 points every year almost. And that's a low estimate, depending on who you talk to. So the fact that data centers as a whole are driving the heck out of that edge, right? The power delivery edge, if you will. The cadence at which we used to develop solutions has absolutely been massively accelerated because of these new needs that are happening because of data center, of different GPUs, and the advent of AI on the whole. So yeah, to answer your question, are we seeing compressed timelines that we need to deliver the next and next and next generation? Absolutely. In some cases by 2 and 3x.
So I'm wondering just, I guess, how you see maybe what's happening in the data center maybe sort of changing the trajectory for GaN as a technology, for instance, since it seems like a lot of companies, including TI, are moving from more of a hybrid situation in traditional power supply units where there's silicon carbide and GaN, or maybe silicon and GaN, to more all GaN, or at least majority GaN systems?
That's an excellent question. And yes, I mean, if you think about what power switch reigns supreme, if you will, it's generally the one that takes the least amount of energy to turn on and the least amount of energy to turn off reliably. Today, from a technology standpoint, that is GaN, bar none. It's not silicon carbide, it's not IGBT, it's not silicon. And as a result of that, knowing exactly that we're just on the start of a power delivery roadmap, right? From a power density standpoint, you pick the best device you can. And that today is GaN. This is the reason why. It's a very real thing that you're talking about. Even a few years ago, I would be talking about other technologies in this space. Today, when I have conversations, it's all GaN for that reason. Because if we want to get more and more power density, there's only two things you can do. You need to switch everything faster, lose less power when you're doing it, and as a result of that higher frequency, you can get smaller and smaller magnetics, passives, other elements that then get you a reliable, high density power converter solution. So yes, it's GaN, that's what I'm seeing everywhere from, you could say, starting at the 800 volt rail all the way down.
Okay, so my last question relates back to what I was asking about, sort of the influence that data center and data center innovation is having on the power electronics space. Are there areas where you see maybe innovation or at least investment maybe being constrained around the industry as more focus shifts towards the data center and sort of fulfilling the needs of that market?
That's a great question. I can't actually talk to specifically what is happening everywhere, right? But I will tell you that the speed at which this particular market segment seems to be growing and seems to want to grow over the next few years is fairly unprecedented. There are going to be challenges, as there are with anything that is growing that fast, but I don't know that we know all the challenges that are coming our way yet. What I will tell you is that, at least from our perspective, a lot of the investments that we've been making for many years now feel like we're completely geared to match the moment, to meet the moment, if you will. So that's something I can tell you about, because right now, in terms of just capacity investments in the right places for power semiconductors, I feel pretty good about where we are.
Okay, Kannan, thanks so much for taking the time to speak with me and walk through this.
Thank you, James. Pleasure.